We're going to talk about what happens to things when they're undergoing constant acceleration now. And things undergo constant acceleration all the time around us, provided air resistance is negligible, because that's what gravity does. It took a long time to realize that air resistance was an important feature of falling things. Aristotle used to think that heavy things just naturally fell faster than light things, which looks like a reasonably good result of that experiment. But it's not necessarily the heavy thing and the light thing are acting differently under gravity there, because he didn't think about air resistance. Galileo put forward a sort of a thought experiment that made Aristotle's idea that heavy things fall faster than light things seem a little strange. He said, suppose you have one cannonball and another cannonball exactly like it. All right? So because they're the same, they'll fall the same. Now, if we had a bigger cannonball instead, you'd expect that to fall faster, according to Aristotle, because of gravity. Well, suppose you have those two cannonballs, and instead of having one twice as big, we just had those two attached by a little chain, like just a tiny little hair. That's now a bigger thing, right? So when I drop it, it should fall faster. But we know that if we attach two cannonballs by a hair, that's not going to change how fast they fall at all. So that goes against our intuition. Oh, says Aristotle, okay, you have to make it thicker. They have to be properly attached, all right? Well, how thick does it have to be? Does it have to be just a rigid little chain? What if I put a tiny dob of glue between them? Do they suddenly fall faster now? That doesn't really work with our intuition either. And in fact, what we understand now is that air resistance is really important in understanding why heavy things seem to fall faster. If I have my piece of paper, then it falls. It's falling because of gravity, but it's also being pushed up by the air. And the main reason that this pen falls faster than this piece of paper is because of the air resistance. And you can test that by taking the air away. And then when you've got no air resistance, you see that these two things will in fact fall at the same rate.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So that's got to be absolutely the world's most expensive version of that experiment ever. And yet it wasn't even in HD. You can get the same effect just by putting things in a vacuum tube and sucking out the air. Now, Galileo didn't just think about gravity and say, I don't think Aristotle can be right. He actually went and did the experiment. And when he was doing the experiment, he didn't have really great clocks, and things fall pretty fast, so it's hard to get accurate time measurements. So he slowed things down by putting things on a slope and rolling them down the slope. And he tried different slopes, and he found that indeed gravity caused things to accelerate at a constant rate. So to keep things simple, we'll just start by considering motion in a single direction. So we have some object that's got a position we can define, and it's traveling in some direction. It's really important in your diagrams to be as clear as you possibly can. And so we're going to have a before diagram and an after diagram. And you'll note I've explicitly said after a time t for my diagram, so I've kind of defined my symbols in my diagram, and that's good practice. So after a time t, it's going to be somewhere else. Now, in order to figure out how it's going from one to the other, we need to know its acceleration, and we also need to know its velocity. Just because it started on the left, and so it started with a negative position, doesn't mean it was going to the left. It could have had an initial velocity where it was heading to the right. So let's look at the initial velocity. So the initial velocity is a vector. It's got a direction, so it's either positive or negative if we're going in one dimension. And we're going to call that u. So that's its initial velocity. And we're going to have a final velocity. And the final velocity could go in either direction. I'm just going to draw it to the right, assuming that it's going to be positive for the purposes of this diagram. And of course, the reason we're working all of this out is that we've got an acceleration. So after a time t of acceleration, and again, I'll direct that to the right, assuming the acceleration is in the positive x direction. Let's look at what happens graphically before we worry about the algebra. And so you have the acceleration doing nothing at all over time. So if I have time on one axis and acceleration on the other, we've already drawn on our diagram that it starts at a value of a, and it does not change. That's our idea. We're talking about constant acceleration. So it's like that. We've drawn it above the origin because our diagram has it as a positive number pointing to the right. Now what happens to velocity? Well, we know that the velocity is changing at a constant rate. So it starts at u at time t equals 0, and then is going to increase, because our acceleration is in the positive direction, it's going to increase up until it gets to our final value of v. And that should be a lovely straight line. I've drawn a reasonably straight line. Now what's going to happen to our position if that's going on? Well, we start at a negative value on our diagram, so I'll have that there. So that will be our x0. Now if I'm going to write x0 on there, then I should write an x0 on here. Always have things defined on your diagram. And if we're going to be moving and we end up at x final at a later time. Now what's this shape going to look like? Well, it's going to start off at some slope. And the slope here is going to be the slope given by our initial velocity, which is u. So if we break this up into a small amount of time, delta t, then we know that the velocity is the distance traveled over the time, and so the distance traveled is going to be the velocity times the time, or u times delta t. And up at the end it'll work the same, except the velocity v is larger than u there, so the slope should be steeper. And somehow those slopes have to match, and so if we try and smoothly connect those curves, it's got to look something like that. Okay, let's do the algebra for that. So we know that the acceleration is constant, and we know the definition of acceleration. So it's the change in velocity divided by the change in time. And so the change in velocity is going to be the final velocity minus the initial velocity. And the time taken we've written down as just t. If we multiply both sides by t, so if we multiply the left by t and the right by t, it's going to cancel that. And so we'll end up with at equals v minus u, and we can rearrange that. The most common way of arranging that one is as v equals u plus at, just adding u to both sides. So that's the first equation we often remember when we're talking about constant acceleration. That relates the final velocity to the initial velocity and how much you're accelerating. It's a little bit harder to figure out where we're going to be because our velocity keeps changing. So let's just look at a particular time in the middle where we've got, say, a velocity v1. At that time, if we look at a very small amount of time, the velocity won't change very much. And so if we just take a small amount of time, delta t, then we know that the distance it's going to change is going to be delta x, is going to be v1 times delta t. And v1 times delta t is basically just a little rectangle that big. It's the area of that rectangle. And what we have to do is we have to have the little change in distance we get from that piece, and the little change in distance we get from that piece, and so on and so on. And that turns out to be just the area under this curve. That's how far we go. And again, you can do that formally by going to calculus, but if you just believe me that that's the area, and you can kind of see it, it's just the sum of all those little rectangles, then it's the area of this rectangle plus the area of this triangle. And the area of this rectangle, well, that height is u, and this length is t, so that's just u times t. And this height is v minus u, and that length is t, so this is going to be half of the product of those. So it's v minus u times t, that's the size of that big rectangle there, and because it's the triangle, we're going to have half of that. So we're going to have to add this area and that area together to get the distance that we travel. So the distance we travel is the final position minus the initial position, and we've just agreed that it's going to be this ut, the area of the rectangle, plus v minus ut all on 2, which is the area of the triangle. Alright, so I'm going to introduce a symbol which everyone else uses, which is just s, the total distance traveled. And then I'm going to plug this velocity here into there. In fact, it was particularly easy because we already had v minus u, so we could just go straight in and plug in our at. And that's the second equation we use to describe how things move under constant acceleration. And so we can see this curve here is quadratic because it goes as time squared. Now there's a third equation that people use, which is really just a rearrangement of these two. What we're going to do is we're going to try and eliminate time. And so from this equation here, if we divide by acceleration instead of by time, we get, and then we're going to plug that into here. So we just expand out the first bracket and then the second bracket. And then we note that that term cancels with that term. And we note that this term half cancels with that term. And we've got two things left. And if we multiply both sides by 2a, And that's our final equation relating the initial and final velocities and how far you travel for a constant acceleration.